Okay, so in this question, I'll be mainly focusing on the second half of the question, but I'll just start from the start. So, state what is meant by specific heat, specific latent heat. So, this definition, um, so what stood out to me is that instead of writing thermal energy to change state of a kg of a substance at a constant temperature, you have to say thermal energy per unit mass to change state at a constant temperature. And apparently the word 1 kg is not accepted. So this is something to be careful of. And also instead of thermal energy, I guess you can also write heat transfer. So you can write like heat transfer per unit mass to change the physical state of a substance at a constant temperature. Okay, so moving on. Okay, question B. A student determines the specific latent heat of vaporization. So when it's saying vaporization, what we know that is that it's trying to convert a liquid into gas. And let's keep reading. So this is our apparatus. So we have a heater over here. It's releasing some heat into the liquid. And well, I guess in the process of heating, there will also be heat loss to the surrounding as well. Because well, if you try to imagine it, let's say we're in like a normal room right now, and the room is probably like maybe like 225 degrees Celsius, but this liquid right here, okay, if you continue reading, you'll see that when the liquid is boiling at a constant rate, this means that the liquid is at 100 degrees Celsius constantly while the heater is on. So because of the heating of the heater, the liquid is heated up until it starts boiling to its boiling point. And okay, the balance readings are noted at this intervals. And after 10 minutes, so after like five intervals, 5 2-minute intervals, the current is reduced. What does that mean? So that basically means the power is less strong from the heater, so there's less heat dissipated. So as a result, the heater is cooling down. So we're assuming that the liquid also, it might cool down, but in this case it does not cool down for some reason, which I'll explain later. And they're reading the balance reading. So here they are actually measuring the mass of the water. Why they're measuring the mass actually? So if you see, right, this liquid, it's boiling right now. That means on the top of the surface, the most energetic molecules, they are going to, let me change the color. The most energetic molecules, they will escape the surface of the liquid. And this process is what we call the evaporation. Okay, so here are some readings for us. This is when time is from 0 to 10 minutes. So this is while the heater is on. And the current is a bit larger. And this is after time 10 minutes, and the current is just ever so slightly smaller. So I reduce we have reduced the temperature right here. Okay, so the first question was easy. You just check the graph from here and you can deduce like the mass of liquid evaporated. Okay, this is slightly more challenging. Explain why, although the power of the heater is changed, the rate of loss of thermal energy to the surrounding may be assumed to be constant. So, do you know what the rate of loss of thermal energy to the surrounding is referring of? Well, if you're not sure, this is what we're talking about right here. So, if I redraw the diagram, so right now, the system we have is, this is a system we have. And everything else here is the surrounding. And the energy will be, the heat will be dissipating outwards because the surrounding is obviously like a bit cooler than the 100 degrees water. So this is the rate of, this is the loss of heat we're talking about, loss of thermal energy. But since here, if you go back to the start, we were talking about specific latent heat. If I draw like a normal temperature change graph when the water is boiling, or when the water changes state, well, we can see that this axis is temperature, this is time, and so when we have ice is at negative something degrees Celsius. So as we add more temperature, as we add more heat, the state of the ice is going to, the temperature is going to increase in a constant rate. And at 0 degrees Celsius, it's going to undergo a state change from solid to liquid. So from ice to water, basically. And from here onwards, now it's a liquid. If you heat it more, temperature is going to increase until we hit another flat line. This is where the liquid is being converted to gas. And after it's being converted to gas, by the way, this happens at 100 degrees Celsius. And after it's been converted to gas, if I move on, the gas is being heated even more. And this is the journey we're talking about in this question. This is called the specific latent heat of vaporization. Where now we have a liquid changing its state to a gas. And at this point, the temperature is 100 degrees Celsius. So if you notice, in this entire period right here, in this time interval, the temperature of the matter we have right now, which is a mixture of liquid and gas, a mixture of liquid and gas would look something like this. Wait, this is too dark. So imagine this is the water, and the gas is like releasing out, just evaporating. So this is the system we have right now. And in this, during this time interval, so like this time interval, the temperature is constant, and the system at this point, well, it has, let's say the liquid has a constant temperature. And because of that, if you recall the, so what does, so, okay, the question asks, why are we assuming that the rate of loss of thermal energy to the surrounding is constant? And if we check right here, even though, so as time passed, so let me draw something. This is like T is 0, T is 10, this is like onwards. In this interval, we have an I of, I think it was 1.2 according to my memory. And here onwards, it's 1.10, 1.0. At this point, there's a reduce in current. But the question is saying that the before and after, they have the same energy loss, essentially. So why could that be the case? Well, this could be the case because, well, you see, even though the current has like a slight decrease, it does not, since we have like a period of time that we have a constant temperature, even though the decrease of current might have taken place, we're still having boiling water right here, and the temperature of the water isn't going to change despite the increase in temperature. So despite there being like, this is a heater, for example, it's still releasing out like heat, to the water. Despite that happening, the temperature of the water itself is not being increased because it's at this point where, the temperature of the system is constant. If the temperature of the system is constant, and let's just say that it has already established an equilibrium with the surrounding. If there's already like an equilibrium right here, let's say they both happy and the thermal transfer is, going both ways equally right now because I've reached the thermal equilibrium. Well, then if the water has not changed its temperature, obviously the surrounding also doesn't change its temperature, right? Because it just makes sense. And this is a region in contact. Since the region in contact, well, in reality it doesn't look like this, but the beaker itself is a region in contact. And since this region in contact is not changed, and the temperature of the system inside here is not changed, the temperature of the surrounding will also not be changed. This is kind of the explanation for this question. So, if I refer to the Mark scheme, this is what the Mark scheme says. The temperature difference between liquid and surroundings does not change. It's a 1-mark question, by the way. So the temperature difference between the liquid is a system, by the way, and the surroundings, I would say the surroundings will be the air. Does not change. And so this would be the system. Let me relabel this in a different color. Okay. So just as a summary of my explanation right now, just now, the temperature difference between the liquid and the surroundings does not change. And why is this? It's because the temperature of the liquid is not changing at this, despite the change in current. Why is this the case? Because now we're at the specifically latent heat of vaporization, and in this period, our system, liquid, has a constant temperature despite the temperature increase, because it's a boiling water right now. So, and if the system has a constant temperature, if let's say the system is in thermal equilibrium